Hello and welcome. This presentation is about transaction management. We will cover the asset properties and different transaction states that are important in understanding how databases ensure data integrity. So, what exactly is a transaction? A transaction is a logical unit of work. It must be either completely executed or completely undone. Consider it as a single, indivisible operation. It's important to maintain database consistency and ensures reliability, especially when multiple users are accessing the database at the same time. In short, a transaction is a sequence of operations performed as a single logical unit of work. To ensure that transactions are processed reliably, we rely on the asset properties. ACID is an acronym. It stands for atomicity, consistency, isolation, and durability. These properties are essential for maintaining the integrity of data within a database system. Let us discuss atomicity in detail. Atomicity means that all operations within a transaction are treated as a single, indivisible unit. It's an all-or-nothing execution, which prevents partial updates and is implemented using rollback mechanisms, maintaining data integrity during failures. For example, if you are transferring money from one bank account to another, either the money is deducted from the first account and added to the second, or neither operation happens. Here is a simple bank transfer example. We begin a transaction, then update the accounts and finally commit the transaction. If there is a failure in between, then we roll back. Consistency ensures that a transaction brings the database from one valid state to another, maintaining all defined rules and constraints. It preserves database integrity constraints, enforces business rules and logic, prevents invalid data transformations, and maintains referential integrity. Think of it as ensuring that the database follows all the rules before and after the transaction. A transaction moves the database from one valid state to another valid state. This ensures that there are no intermediate invalid states. Isolation ensures that concurrent transactions execute as if they were running sequentially, without interference. This prevents dirty reads, avoids non-repeatable reads, and eliminates phantom reads. It is implemented using locking mechanisms and offers various isolation levels. Imagine multiple people trying to book the same seat for a concert at the same time. Isolation ensures that each transaction is separate. In that way, they don't affect each other so that only one person gets the seat. Durability guarantees that once a transaction is committed, its effects persist even in the event of system failures. It makes sure that changes survive system crashes, and it is implemented using write-ahead logging, utilizes database backups, ensures data persistence, and prevents data loss during failures. Once a transaction is completed, the changes are permanent, no matter what happens to the system. This is often achieved by writing the changes to a log before applying them to the database. In the event of a crash, the database can recover by replaying the log. Now let's look at the different states that a transaction goes through during its life cycle. A transaction moves through various states during its life cycle. It begins in the active state, transitions to partially committed after its final operation, and then to committed once changes are permanently stored. If failures occur, it enters the failed state followed by aborted after rollback. All transactions eventually reach the terminated state. Here are the details on transaction state transitions. First, we have the active state. It is the initial state where the transaction is executing read-write operations. Next is the partially committed state. This is after the final operation is executed, but before changes are permanently stored. Then we have the committed state. In this state, all changes are permanently stored in the database and cannot be undone. And finally, the failed state transitioning to aborted. When normal execution can't continue, the transaction enters the failed state, and then aborted after rollback. We can see it in the example code. We begin the transaction, that means it is in the active state. Then select Balance from Accounts and update the accounts which is still active. After the final operation, it is partially committed, and the command commit means now it is committed. If there is an error, then rollback command makes it go to failed, then aborted. To summarize, transactions are fundamental to maintaining data integrity in databases. The asset properties, atomicity, consistency, isolation, and durability ensure reliable processing of transactions. Transactions move through different states, reflecting their life cycle from active to committed or aborted. Implementation mechanisms like concurrency control, locking, logging, and recovery procedures are critical for robust transaction management. Overall, proper transaction management is essential for reliable database systems. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.